Hey everyone. So in this video, I like to talk about the even and odd identities for sine and cosine. And so before I even bring up sine and cosine, let me define what it means for a function to be even or odd. And so here, let's start with even. On the right side of this page here, I have the graph of the function f of x is equal to the absolute value of x. And so here, this is an example of an even function. And what I like to point out is that there's symmetry in the graph of this function. That here, the graph looks identical on the left side of this y-axis as it does on the right. And if we were to reflect this graph over this vertical line, we would actually end up with the same graph as what we started with. And so this is what we mean. This is an example of an even function, is that if we were to reflect the graph over the y-axis, we would get the same function as what we started with. And so how can we make sense of what this would mean or suggest algebraically? Well, the idea is that if I look at some value of x, maybe I'll just label it here. I have this choice of x that I've highlighted in pink. And I look at the function value at that particular x value. Well, I would get the same result as if I were to plug in the negative of the x value is what I started with, right? So here, if I were to look at the negative of that original x value of what I started with, the opposite x value, and I were to look at the result of my function here, I would get the same y value, the same result. And so here, algebraically, that reads as f of negative x. Right, if I were to take the output, the y value, from plugging in the negative of my input, well, that would be the same as just my original output for my original input. And then really, if I were to say that f is an even function, what that's really saying is that if I negate the input, my function doesn't really care so much. And we can kind of see that here in this absolute value of x function. Whether I plug in an x value or it's negative, we're going to get the same result anyways. And so this is kind of helpful sometimes when we're dealing with even functions, is that if I see a negative of my entire input, I can just sort of forget that negative sign. Kind of gives us a way to simplify a function or manipulate a function in a way that we wouldn't have been able to do before. Okay, so what does it mean for a function to be an odd function? Well, here, let's take a look at this example of an odd function here. G of x is equal to x cubed. This is an odd function. It's not odd because of the exponent. It's actually odd because of the symmetry in the graph. And so what kind of symmetry am I talking about? Well, this graph here, it's symmetric about rotating 180 degrees around the origin. So if I rotate this graph 180 degrees around the origin, we actually end up with the same graph as what we started with. And maybe I'll show you, if you can't see it already, maybe let me take this, I'll rotate to the right 90 degrees, I'll rotate this graph again to the right 90 degrees, and it looks identical to what we started with. I mean, the numbers are flipped around because we've rotated, not exactly all the way to what we've started with, but the graph looks essentially the same. Another way you can sort of talk about or define the symmetry for an odd function is that if you reflect the graph over both the y-axis and the x-axis, you'll end up with the same graph. And so let me do that as well. So if I take this graph here, and if I reflect it, I flip it horizontally, so over the y-axis, and then I flip it vertically as well, so over the x-axis, well, we ended up with the same function we started with. So here, these are two ways of making sense of what it means to have an odd function. There's sort of these two different kinds of symmetry involved. And so, we talked about an algebraic way to identify an even function. What's an algebraic way to identify an odd function? Well, the idea is that if I look at a particular x value, maybe I'll look at this one here, so let's say this x value, and the resulting output, If I look at the negative of that x value, so here this will be negative x, and the corresponding resulting output, the idea is that we'll get the same result, but just the negative of one another. And so here, really what I mean is that here g of x is an odd function, and algebraically that looks like if we take g of, if we negate the input, if I negate my input, so I'm looking at this particular x value, and then I look at its output, well, it's going to be the negative of our original output, right? So here this was a little bit more than 2, and the output we ended up with was a little bit, or it's the negative of that quantity, right? So now it's a little more negative than negative 2. So really all this is saying here is that if we negate the input, that's really equivalent to negating the output for an odd function. And so again, if we see, and if we're dealing with an odd function and we see that the entire input is negated, we can imagine actually pulling that negative sign out, for example, which is not something you can typically do with functions. Okay, so let's go ahead and bring these ideas to our sine function and our cosine function. So let's start with this function here. First things first, just to get a little bit more practice with identifying sine and cosine. So which of the two trigonometric functions is the graph that we have here? Well, here this is a cosine function, right? Cosine functions, they sort of start at an output value of 1 on the vertical axis, and then if I'm kind of looking from left to right, well, it starts at the peak and it sort of works its way down towards its lowest most point and then back up. Right, so here that's an example of a cosine function. So I'm going to write this as y is equal to cosine of x. And then, here we're talking about even and odd functions. So here what example is this y is equal to cosine of x function? Is it even or is it odd? Well, it looks like it's symmetric about the y-axis. If I were to flip this this graph over this vertical axis here, we would end up with the same graph as what we started with. And so here, this is just saying that if we take cosine of, the negative of some input, this is really the same as cosine of the non-negated input. Negating our input for our cosine function, because it's an even function, isn't really going to do anything. And maybe let's take a particular example just to really illustrate this. For example, if I take cosine of negative 2 pi over 3. So here, what is cosine of negative 2 pi over 3? Well, negative 2 pi over 3, that's 2 pi over 3 in the clockwise direction. This is 2 pi over 3. We end up with a 30, 60, 90 triangle. And so here, cosine is giving us the x coordinate of this point, and that's this measurement here. And so on this 30, 60, 90 triangle, it's the short side length of this triangle. That's negative 1/2. This is equal to negative 1/2. And here I want to show you that this is going to really be the same as if we were to plug in cosine of 2 pi over 3, the non-negated value. So here this is going to give us, if we sort of look at our unit circle again and we look at 2 pi over 3 in the counterclockwise direction. Oops, sorry about that. Well, we end up with the same 30, 60, 90 triangle, but just above the x-axis. And so when we're looking at the x-coordinate of this point on the unit circle, well, it's going to have the same x-coordinate as the one on the bottom side of this unit circle, right? Really, the x values are this side length here, and it's the same regardless of whether we're looking above or below this x-axis. And so here we also get negative 1/2. We get the same value regardless of this negative sign here. Okay, so what about this function here? Well, we already identified that the previous example was a cosine function, so maybe let's not go through the motions of identifying that this is a sine function, but what's the reasoning behind why this is a sine function? Well, it's because here it's sort of starting at this vertical intercept value of 0, sort of in the middle of all of the y values here that this function attains, and then it sort of works its way upwards towards one of its peaks, and then back down towards its sort of low point, and then back up. So here, this is an example of a sine function where its vertical intercept is sort of at its middle. Okay, so this is an example of y is equal to sine of x. And so here, this is not an even function because we said an even function is symmetric about the y-axis. If we were to flip it over this vertical axis, we would end up with the same graph. Well, that's not true for y is equal to sine of x, so it's not an even function. But it is an example of an odd function. Right? So if I were to rotate this graph 180 degrees about this origin, we would end up with what we started with. And maybe just to really showcase this, I'll sort of do the same thing I did with the previous odd function. I'll rotate. So I'll rotate right 90 degrees. Ooh. Let's try this again. Rotate right 90 degrees. So it looks the same, right? Just kind of flipped around, or the axes look like their labels are flipped. Okay, so here, so the sine function is an odd function. So sine of theta is an odd function. And so maybe let's do the same thing we did in the previous example. Let's showcase with one particular value just to really illustrate the point. So if I take, let's look at sine of 7 pi over 6. And then let's look at what happens, what do we get out when we negate that input. Well, sine of 7 pi over 6, 7 pi over 6 is, well, it's here on the unit circle, right? Pi over 6, or 30 degrees past the opposite side of the circle, past pi. And so here we end up with a 30, 60, 90 triangle. And here sine is giving us the y coordinate of this point. So it's this distance here. It's this negative 1/2. So we get negative 1/2 again, I guess. But that's okay. Now if we look at sine of negative 7 pi over 6, well, we're going to do the same thing, but we're going to look at the angle that's obtained by rotating around our unit circle in the clockwise direction. And so here we end up with a 30, 60, 90 triangle, but above the x-axis, right? Again, 30 degrees past 180, but just past in the clockwise direction. And so here sine is again giving us the y coordinate on this unit circle, and the y coordinate is given by this short side length of this 30, 60, 90 triangle, and it's 1/2. So here we get positive 1/2. And so really this is just showcasing that sine of negative 7 pi over 6, when we negated the input, when we negated 7 pi over 6, we really just obtained negative of the original output. All right, so here the original output was negative 1/2, right? Sine of 7 pi over 6. This was negative 1/2, and then really what we're saying is that when we negated the input, really that amounted to negating the output. We obtained negative 1/2, giving us positive 1/2. And so maybe to say that a little bit more concisely, or in the way we will usually see when we're dealing with expressions or using our even or odd identities, is that sine of negative theta is the same as negative sine of theta. This is really just saying that sine of theta, the sine function, is an odd function. So what about the tangent function? Is the tangent function an even function, an odd function, or neither? And so I guess I should say also that there are many functions that are neither even or odd. We covered a handful of different examples of even and odd functions, but there are many functions which don't display the symmetry we saw in the previous examples. There are many functions that aren't reflective, symmetric about the y-axis or about the origin through rotation by 180 degrees. So with this tangent function, let me ask you to pause the video and try and see if you can convince yourself one way or the other, whether it's even, odd, or neither. So one way we can argue that this tangent function is actually an odd function is by writing this function in terms of sine and cosine. So to argue whether a function is even or odd, we want to make sense of what happens when we plug in the negative of a particular input to this tangent function. So tangent of any angle is the same as sine of that same angle divided by cosine of that same angle. And so here, if we look at this cosine function, cosine of negative theta, well, we know that cosine is an even function. And so really inputting the negative of some angle into our cosine function, well, cosine doesn't really care about that negative sign, and we really end up with the same as if we didn't negate that input. This is the same as cosine of theta. And then sine is an odd function. And so what does that mean? That means that if we negate the input, that's really the same as negating the output. We can really re-express this and we'll get the same result as a negative sine of theta. Negating the input is equivalent to negating the result of this function, negating the output. So in other words, taking sine of theta and negating it. And then here, this is almost the tangent function, but it's got this extra negative sign, right? So really this is just the same as negative tangent of theta, and that's exactly what it means for a function to be odd, right? So here what we're saying is that tangent of theta is an odd function. In other words, tangent of negative theta, if we negate the input, we really are doing the same thing as negating the output. It's negative tangent of theta. And so let me go ahead and show you a quick way we can use these ideas to sort of simplify an expression, to manipulate some expressions. And so here we've got cosine of negative x. We're subtracting away sine of negative x, and we want to simplify this. So here, cosine of negative x, kind of using the same ideas as we did in the last example. Again, this is an even function. And so really, this first part of the expression, it's the same as cosine of just x, right? Cosine doesn't really see that negative sign. It gives you the same result whether that negative sign is there or not. And so we might as well, or we can, for our convenience, write it without that negative sign. And then similarly, well, sine is an odd function, and so here, sine of negative x, that's the same as negative sine of x. Right, so negating the input is the same as negating the output, so really seeing that negative sign inside the input, I can see it instead in the output as negative sine of x. And so what can we do with this? Well, now we're subtracting away negative sine of x. Subtracting away a negated thing is the same as adding it. So this is really cosine of x plus sine of x. So really, what we did here was more or less identical to what we did with the argument for showing that tangent was an odd function. But I just wanted to showcase as well here that we can manipulate expressions using these ideas as well.